This is the first video in one variable statistics. And of course the first question is, what does one variable statistics mean? Let's look at an example. Let's perhaps consider a fascinating question of how much yak cheese can a yak produce? Inquiring minds want to know. And of course, if you want to answer a question like that, the first thing you have to do is collect some measurements. And to do that, you have to know a time frame for a question like this. So perhaps how much yak cheese can a yak produce per year. So we're going to find a bunch of yaks and keep track of how much cheese is produced from each yak. And we measured it in, of course, kilograms of cheese in 1 year. Now we can start trying to figure out the answer to this question. But of course, are all of the yaks producing the same amount of yak cheese? The answer is no. So it's going to be a little bit harder to answer this question because there is in fact a distribution of values. That makes it a little bit more fun because when we have a distribution, we can actually talk about several different aspects of that distribution. We have the shape of the distribution, we'll get into that in a little bit. And of course, center is the classic one that most people think of, which is average. There are several measures of average, mean, median, and mode. We can also talk about the spread of the distribution, how far the data tends to be away from the center. And then we can talk about something called outliers, which are really weird values. Are there really unusual numbers in this data set? And we can also identify particular positions within the distribution. You might be familiar with percentile. You know, what's the 85th percentile for yak cheese? And this all works for what's called quantitative data. What is meant by quantitative data? We can do things like add up all of the measurements, and then we can divide by the number of yak and get this average of 37.81 kilograms per yak. And that would be our center or average. That would be one measure, but of course not all of these numbers are 37.81. So it's a more complicated answer. Now, if it's not quantitative data, what is it? Well, we can have a little example here about M&Ms, right? We have 10 blue M&Ms, 30 green M&Ms, which we could try to do the same kind of thing. We add them to be 40, and we could divide by, I have no idea what. Can we really average color, blue and green? It just doesn't make sense because, of course, this is not quantitative, it's categorical. We have these two categories, the category of blue and the category of green, and it really just doesn't make sense to try and average blue and green. It doesn't work. So that's an example of categorical data. We have to deal with categorical data entirely differently. All of what we're going to be doing in most of this unit, except for the very end, is going to be quantitative data. So now, let's rewind a little bit and get back to our yaks. And this is kind of the overview part because really there are going to be two systems for analyzing this distribution of values. Right, and these are kind of the pictures, the graphical representations. We have this one that kind of looks like boxes, and this one which has these two whiskers, which of course is why this is called a box whisker plot. And this one is a histogram. You might have seen histograms in the past. We can talk about, of course, our centers. They have different means. When you deal with histograms, you're going to use means. If you're dealing with a histogram, you would not use the median because that's not the system, right? Medians go with box whisker plots. And then we can also talk about spread, right? Standard deviation goes with the histogram where IQR goes with the box whisker plot. Right? When do you use one system versus the other? Well, it kind of depends a lot on whether there are outliers because here are some terms which you will need later on. System number one is called a non-resistant system, or system, I suppose, in which outliers can be a problem. System two is called a resistant because outliers really don't pose as much of a problem. So now, if we go back to our original question, we can actually produce, all right, we're going to deal with, right, the histogram mean standard deviation system initially, right? These are kind of the 5 things that I listed before, right, that we can talk about when answering this question. For this particular video, we're just going to deal with shape. Right? We're going to deal with the other ones in other videos. Right? And so here's the histogram for this particular data set. Now the question is, first, how do we produce this histogram? Because that's something you're going to have to do. So producing a histogram, what you need is a frequency table. What is a frequency table? Well, we have intervals here, which contain all of the data. Notice that there is no data that is -5 or less, and there is no data that's bigger than 85. So all of our data should be in this range. And we'll talk about how you come up with these intervals in a little bit. But what we need now is to go and say, well, how many data measurements are between -5 and +5? And I forgot to mention the fact that these intervals define the boundaries of these boxes as they come up. And an important point, actually, is that this is a continuous number line. Right? And so there aren't any breaks. Right? If you have 5, you know which interval it goes in. It actually goes into the first one. If you have 6, it's into this one. Every number is actually covered. It's a continuous number line. Now, going back to the first interval, how many data measurements are between -5 and +5? Right? Looks like there's really just that 0. So under frequencies, only one number is between -5 and 5. Right? Which means that's why that first column is a 1 unit high. Right? How many are in the second interval? Well, it looks like just 1. We have, looks like 2 in the next interval, then 3 and 5, back down to 3, down to 2. There are actually no measurements in this interval, which is why there's no box there. And then finally in the last interval there's only 1, and so we've produced our frequency table and our histogram. Now let's talk about the shape. The name of this shape is called mound-shaped symmetric. Right? And you can kind of see this because really there's this mound shape. Right? And it's relatively symmetric. Is it perfectly symmetric? No, there's some asymmetries, but that's okay. What we want is that it's approximately mound-shaped symmetric. This is statistics. There is no perfect anything. So what we're looking for is trend. We're looking for pattern. Right? And this is a mound-shaped symmetric pattern, which of course you can see actually in the frequencies as well. Now, how do we know we've got all of the data in the frequency table? Well, if we add up our frequencies, right, we get 18. And notice, if we were to come over here and count how many there are, right, there are 18 values. And so those numbers match up, and we know that we've got all of our data. Now, this number 18 is actually a pretty important number, so important that it's actually given its own letter. This is N, which is usually known as the sample size. That comes in a lot of different ways. Now, what we want to do is see where did we come up, or how did we get these intervals? And this is something you kind of have to play around with. And what you really need to do is use your TI-84 calculator. And this is going to help us get what we need. If we go into Stat and Edit, you can see that I've already entered in all of this data. So the calculator can actually make histograms for us, which is really very nice. Now, important, we have to set up our window settings. Now, what we can do is I can set up, Xmin. Now, Xmin is this very far left part. I could put -5. A common error is if you put -5, the calculator doesn't like that. This is the negative sign. So that's our x min. Our x max, we could put our 95. That would work fine. Now, x scale is particularly important. It's the what's called class interval. It's the width of the box, which in this case we're using a width of 10. Right? And we can figure out the minimum. The y is, of course, up, down. We can use, maybe -1. I do like a little space on the bottom. And maybe go up to 6. We already kind of know what it's looking like. X scale can be 1. It's actually not too important. And X res also not particularly important. If we hit graph, we don't see anything, because what we need to do is go over here to stat plot, right, and set up the graph itself. So you can see I go second stat plot, and there are 3 plots that can be done simultaneously. We only want to do 1. So we'll go to number 1, and that gets us the setup menu for the first statistical plot. I want to turn it on, so I hit enter. And it comes over here. You'll notice all these different types. The first one is a scatter plot. And you can see over here, this is clearly a histogram. So I go down, and I move over to histogram, and select that. All right, notice that what's down here changes depending on what type you use. Go down here. XList is our original data, really. There's 2 ways to enter this data. We could actually enter the frequency table itself. I can show you that in a moment. But here I put in the data in L1. The frequency with number 1 would be the number 1 because there is no sort of frequency side. Notice that in the table we do have frequencies, but original data we don't. And now if we hit graph, there we go. We see the exact same histogram. And we've reproduced what I did over here. Now, we're going to go back to the question of how do you figure out the interval width? Well, I can go back to my window. And what happens if I use an X scale of 5? If I hit graph now, all of a sudden I get a different graph. And if I hit trace, notice that, in this first, and I can maybe jump over here, well, start over here. Instead of going from -5 to +5, which is a width of 10, it goes from -5 to 0, which is a width of 5. Well, that's what this X scale does. It changes that width. If we, make this 3, keep making it smaller, notice it keeps spreading things out more and more. And if you hit trace, now we're going from -5 to -2, width of 3. Now, to make things a little bit more complicated, if we wanted to, we could actually change this. We know that the minimum value is, in fact, 0. So we could change that to 0. And that actually changes the graph, too. So we can keep changing our starting point and our width, and we kind of get different distributions. And you play around with it. And, maybe we could make this, instead of 10, make it big, make it 15. And now it gets boxier and boxier. And in an extreme case, like if we went, 25, this will probably give us, really not as much detail. And of course, we'd have to increase the line. Now we can see the top of it. Because, of course, now we have these big 0 to 25, and we're grouping the data by larger intervals, which means the count within each interval is going to go up because we're capturing more of the data. And in sort of in a ridiculous kind of way, we could, go by 75 or something like that, and then it's just, you lose all pattern. It doesn't make any sense. So what you can do is use the calculator to start playing around to see which interval gets you the most or the right amount of detail. And notice here I changed back to 10, but now I changed the x min to 0, right, instead of the -5 like it is over here. So when we hit graph, we get something a little bit different. And if we hit trace, this first one is 0 to 10. Right? And there are 2 in that interval. So I've created actually a different frequency table. And this is really helpful if you want to actually create the frequency table. This is how you do it. Right? And now I can just scoot over. 1, 2, 3, 6. All right, so those are my frequencies for these intervals, and I can just write those down in the table, and I have my frequency table. It's extremely convenient. But notice that, the shape of this, and maybe I'll reduce this again. Maybe I'll make it 8 just to have a prettier picture. It's not the same graph as this one. Right? Is it wrong? Is this one right? Well, I mean, not really. What you're just looking for is whatever graph will give you the clearest pattern. And this one is pretty clear in real life. It's kind of a judgment call as to what's the clearest pattern. But if you do a lot of trial and error, something like this will emerge. Oops. And this has, that's not working. This still has a mound-shaped symmetric. You could identify that as approximately mound-shaped symmetric. Because I'm the one who made the data, I kind of knew that if I started at -5, it would give me an even more clear mound-shaped symmetric shape. But really, either of those would be acceptable. Now, this video is ultimately about shape, right? Creating the histogram is important. Now, if we move forward, right, what are the shapes that actually exist? We have, of course, our mound-shaped symmetric, which does something like that, approximately. We might want to move that over a little bit. Yeah, something like that. Now, what other shapes exist? Right here is uniform. Now, oftentimes you could write this. Right? Here's a perfectly uniform, where this is completely even. Again, is that reality? No. You always get some variations. But what you want to do is think about what's the general trend and what's the overall pattern. Bimodal is something that often confuses folks. In particular, the difference between uniform and bimodal. Bimodal essentially means that the highest and second highest interval, the highest columns, are not next to each other. Right? So it looks like actually maybe this is the highest, and maybe even this is the second highest, and they're not next to each other, so technically bimodal. Well, how about up here? Well, that's the highest, and that kind of looks like the second highest. They're also not next to each other. So what's the difference between uniform and bimodal? Well, really bimodal is talking about sort of clusters, right? And you can kind of clearly see that there are 2 major groupings within this distribution. And that's not really the case up here. This is, you can't distinguish different groups. And so when you use the word bimodal, you're conveying a certain image, that there are sort of groups or clusters of data, right? Where uniform, the image that you're portraying when you use that word uniform is that of pretty much even with normal variation. So that's the difference between uniform and bimodal. We have skewed data, right? We have skewed left and skewed right, which has this sort of swooping kind of nature. How do you know which is left, which is right? It's actually the tail, the short end, which kind of defines the direction of skewness. So here the tail is over on the left side, so it's skewed left. And over here we have a skewed right because the tail is over on the right. And that is the conclusion of shape.